This is my progress video from David Kim. The project aims to model the performance of a Noctua passive cooler, as seen on the screen, to determine if it can successfully decrease high heat levels and maintain normal functionality of a typical computer processor, such as an AMD 5950X, as you can see here. The scenario will be simulated and analyzed in a three-dimensional answers model. From the results, a better design or design suggestions can be made to further increase the performance of the heatsink. The mathematical model will have thermodynamic equations that assume a forced convection due to there being no airflow. Airflow is difficult to simulate in answers and is better suited for CFD. The simplified geometry will allow for these equations to be more applicable, hence the calculations will not be too complicated. This leaves less room for error. Linking back to the simplification of geometry, this is the current geometry of the cooler, and this is a simplified version. It has been simplified greatly to allow for simple modeling as well as a good mesh, as certain geometries will yield lower quality meshes depending on the consistency of the surface of the model. For example, if a smooth surface is immediately followed by sharp corners, then the mesh will not be of high quality. The mesh will be decreased over time while using a hexahedral element size. Hexahedral meshes are economic with the number of elements because the same degrees of freedom for one hexahedron corresponds to 6 tetrahedral elements. Increasing the number of elements will not increase the size of the global finite element matrices, but the computations for one hexahedron is much more economical. Symmetry is applied to the model, as you can see here, on this side and this side. So this is currently using a quarter model. The boundary conditions are, symmetry is applied as this is a quarter model to reduce computational stress and save time. Boundary conditions are currently thought of as energy in and energy out, with heat flow being measured in watts as energy in and forced convection as energy out. Otherwise, there are no other boundary conditions. This is a rather simple model. The parameters of interest are currently the max temperature and the total heat flux. The preliminary results are currently showing a promising trend. It clearly matches how a heatsink should perform when under thermal load. It also shows that the temperature matches with what is recommended online. As you can see here, the base is at around 70 degrees and the tips of the fins are around 60. The online trends recommends maximum temperature ranges between 80 degrees and 90 degrees. Given that the model is under a lot of assumptions and geometric assumptions, it is safe to assume that these numbers are somewhat preliminary and will be expected to increase later down the line in the project and be more accurate to lie in between the 80 to 90 degree range. Currently, at the moment, the model will be experimented on with other materials and different geometries. Hopefully, this will show that the temperatures are closer to the actual range of 80 to 90 degrees. In the final model, the only thing that is missing is, as I mentioned before, the experimentation with different material combinations, element sizes, and perhaps looking into different FEA functions as well. Thank you for listening.